In this video, we are going to be looking at acyl chlorides. We have looked at acyl chlorides before briefly when we did the Friedel-Crafts acylation of aromatic compounds, but now we're going to look at them in more detail in terms of how we make them and other reactions that they partake in. Right, so first things first, what do I mean by an acyl chloride? So let's have a look at the functional group for an acyl chloride. So it's very similar to a carboxylic acid, so you have the carbonyl group there, and where you'd have the OH attached, you now have a chlorine attached to that. So this part here is the acyl chloride functional group, so the chlorine is directly attached to the carbonyl carbon. Right, let's have a look at how we name acyl chlorides. So we start off with the simplest one where we just have one carbon. Given that there's one carbon, it's got to have the prefix methan. Now all acyl chlorides are going to end in oil chloride, like so. Okay, so they all end in oil chloride. The prefix just determined by the number of carbons in the chain. So let's have a look at the next one up. So this one here has two carbons, and therefore this is going to start off with ethan, then oil chloride. So this is ethanoyl chloride. Let's just have a look at a slightly longer carbon chain. Like that. So count the number of carbons: 1, 2, 3, 4. So this one here is called butanoyl chloride, like that. Okay, right, let's now have a look at how we synthesize acyl chlorides, so how we make them. So the synthesis of an acyl chloride. They can all be made from their parent carboxylic acid. So let's just go for, I'm going to go for ethanoic acid. So we're going to be making ethanoyl chloride from this. Okay, the reagent that you need to know for this reaction is SOCl2. Okay, and this is called thionyl chloride. Okay, you can either know the formula for it or know the name for it. Both would be fine. Obviously, SOCl2 is a lot easier to remember. So you react those two together, ethanoic acid with thionyl chloride, and that's going to give you the acyl chloride. So in this case, given that it's ethanoic acid, that's going to give ethanoyl chloride. And hopefully you can see there are other products here as well. So we can see that that's going to be SO2, so sulfur dioxide gas. And you're also going to form hydrogen chloride gas as well, like that. It's cutting off. Okay. So this is the reaction that you need to know for the synthesis of an acyl chloride. Obviously, depending on which acyl chloride you're going to make, you're going to have a specific carboxylic acid. You react that with thionyl chloride. You make the desired acyl chloride plus sulfur dioxide plus hydrogen chloride. And given that it is, or we class acyl chlorides as a carboxylic acid derivative, definition of a carboxylic acid derivative is one that can be hydrolyzed to form the parent carboxylic acid. So I'm just going to show you how the acyl chloride we've just made can undergo hydrolysis. So hydrolysis is the breakdown in the presence of water. and how the hydrolysis of the acyl chloride we just made can form back the parent carboxylic acid. So we just had ethanol chloride. And if we do the hydrolysis of this, in this case we're reacting it with water. And this is going to reform, so the hydrolysis is going to break that bond there, and we're going to reform the carboxylic acid, in this case ethanoic acid, the parent carboxylic acid, and you are also going to release HCl gas as well. And this reaction here is actually quite a vigorous reaction, so that hydrogen chloride gas is quite fumey when it's coming off. Okay, so that's us showing that acyl chlorides can be broken down using water to give the parent carboxylic acid back. Right, let's have a look at why we now form acyl chloride. So obviously one reaction we've done in the past is where we react it with an aromatic compound to form or attach a carbonyl group to directly to a benzene ring. There are other uses for it, and those uses are usually to form esters. Okay, so again, we're going to be forming esters, but now rather than using a carboxylic acid, we're going to use the acyl chloride that we make from that carboxylic acid. Okay, so we can use it, we can use acids to form esters, and we'll do an example now. So if I just use that same carboxylic acid as before, sorry, the same acyl chloride as before, okay, I can now, rather than using a carboxylic acid and an alcohol, I can use an acyl chloride and an alcohol. Okay, and that is now going to form my ester and it's also going to release, as you can see, we've lost Cl and H. That's also going to release hydrogen chloride gas in that process as well. Okay, so we've done ethanol chloride plus methanol, and that's given us methyl ethanoate and hydrogen chloride gas. I'm just going to keep that as HCl for now. Okay, so just want to point out a few things. We haven't in this process used an acid catalyst. So usually when we do the esterification reaction, we use an acid catalyst and we heat it up. In this case, when we use an acyl chloride instead of a carboxylic acid, we do not need to have a catalyst, we do not need to have or we do not need to heat it either. Okay, so that just kind of goes to show that acyl chlorides are more reactive than the parent carboxylic acid. Okay, so if we want to use mild conditions, it is better to use the acyl chloride than it is to use the parent carboxylic acid. Okay, so I'm just going to write that here. There is no catalyst used in this process here. Okay, acyl chlorides are very reactive compared to carboxylic acids. Okay, I'm also just going to write a general equation underneath. So you can have acyl chlorides plus alcohol makes ester plus HCl. Okay, so that's the kind of general equation for acyl chlorides to form esters. Okay, another reason why we use acyl chlorides in this process to make esters is because usually if we want to, so when we use alcohols to form the esters, so far we've just gone for normal alcohols. If we want to do a reaction where we react it with phenol rather than alcohol, so let me just do an example here. So rather than an alcohol, I use a phenol, like that. So I've got my carboxylic acid, got a phenol rather than an alcohol. This reaction here would not happen. Okay. Carboxylic acids are not reactive enough to react with a phenol to form an ester over here. So that's why we use acyl chlorides. Okay, so right here, if I convert that carboxylic acid into the corresponding acyl chloride, this reaction will now happen. Okay, so I can now form an ester over here. Like that. And also HCl is going to be released too. Okay, so I've got my ethanoyl chloride, react that with a phenol. Let's write these down. Again, no catalyst, I just want to emphasize that. No catalyst. The ester that we formed here is called phenyl ethanoate. And we release hydrogen chloride gas there. Okay, so again, acyl chlorides are very useful when making esters between with phenols, because you can't do that using carboxylic acids and phenols. Okay, so when it comes to reactivity, acyl chlorides are more reactive than the corresponding parent carboxylic acid.